As we know, aquatic animals survive in water due to dissolved oxygen. Like fishes, they have a special arrangement like gills through which they can absorb water oxygen from dissolved oxygen from water. So some gases, or mostly the gases, when come in contact with liquid or water or some other solvent, maybe other solvent, they dissolved. They get dissolved, and we have Henry law, which deals with solubility of a gas in a liquid. Suppose, so in this case, the gas is the solute and liquid is the solvent. So, solid solvent system, gas is the solute and the liquid is the solvent. In this case, in this diagram, suppose here we have some solvent like water, and we have introduced a gas above the surface of the water, and this gas molecules, some of the gas molecules are coming into the solution. So this is the dissolved gas, or aqueous phase or liquid phase of the gas, and these molecules remain in the gaseous phase. So this is dissolved gas. Now some gases dissolve to greater extent, and some gases, their solubility is very low. So let us take for example hydrogen, nitrogen, helium, or O2. Their solubility is very low in water. Here we have taken the solvent, water as a solvent. So these gases, their solubility is very low in water, and gases like HCl, SO2, formaldehyde, CO2, methane, etc., their solubility is very high in comparison to these diatomic gases. Their solubility is very high. So in this video we'll discuss the difference, the reason for their the difference in their solubility, as well as other factors which affect the solubility of the gas, like partial pressure of the gas over here is the one factor which determines the amount of gas dissolves. Second factor is nature of the gas, whether it is polar or non-polar, like this. These are polar gases. Some of them like HCl, SO2 are more polar. Methane is non-polar, but it is the reason for solubility is van der Waals forces between the solvent and this gas due to higher molar mass, and low solubility is due to non-polarity. These are non-polar and their solubility is very less. So we'll discuss these things later on in the video. And the third factor, the first was the partial pressure, second was the nature of the gas, and the third factor is temperature. Solubility of the gas also depends on the temperature conditions also. At higher temperature the solubility is low, and at lower temperature the solubility is high, means more gas will dissolve at lower temperature in comparison to that on the higher temperature. So we'll discuss these things in this video. Now we'll discuss the mechanism of dissolution, why and how the gases dissolve. Now the gases, as their nature is, they are moving with a very high speed, and they are striking the walls of the container in all directions, and they are hitting the surface of the solvent with a high speed. Some of the molecules, gas molecules, are captured by the solvent molecules due to intermolecular interactions. Some kind of force develops between the gas molecule and the solvent molecules, and these molecules are captured by the solvent system, and these molecules are, when they come in contact with the solvent, the gas molecules come in contact with the solvent molecules, the intermolecular force will be higher if the gas is polar. So if the solvent is water or any polar solvent and the gas molecules are also polar, so dipole-dipole interaction, or in some cases hydrogen bond, like in case of ammonia, hydrogen bond, or in case of SO2, hydrogen bond will be formed with the solvent, between the solvent molecule and the gas molecules. So this type of gases will dissolve, they will dissolve to greater extent, their solubility will be high. On the other hand, the gases like H2, O2, N2, there is no such force. The only interaction between them is weak van der Waals forces between the solid molecules, that is gas molecule, and the solvent molecules. The force of interaction is weak van der Waals forces. That is why their solubility is low. Now let us answer the question why solubility of a gas increases with increase in partial pressure of the gas. So with the increase in partial pressure, we can increase partial pressure by applying, this is the piston arrangement, and we put some weight over here and the pressure, downward pressure increases. So this same number of particles are now present in a smaller volume. So per unit volume, number of gas particles has increased. So number of particles striking the walls of the container as well as the surface, liquid surface, will increase. So per unit time, the number of gas particles striking the surface of this liquid will increase, and hence the solubility of the gas in the liquid will increase. So more particles will come into the solution when the pressure is applied. And now another factor, another thing we must discuss over here is there is a dynamic equilibrium between the dissolved and undissolved gas. Dissolved gas is constantly coming into the gas phase, and the molecules of the gas in the gas phase are coming into the solution, and there is an equilibrium is set up between the amount of gas dissolved and undissolved gas. Now coming to the Henry's law, it gives a relation between the partial pressure of the gas over here is the partial pressure. Why partial pressure? Because there may be a number of gases. So the contribution of the gas which is under consideration, the pressure contributed by the gas is its partial pressure to the total pressure of the gas. So there may be a number of gases or air or oxygen, nitrogen, hydrogen present in air, and the gas which we are going to solubility of which we are going to study. So the partial pressure of the gas and the quantity or amount of gas dissolved, there is a relation, quantitative relation, which was given by Henry's law. And there are several forms of Henry's law. Their statements vary a little. So let us discuss one by one. The statement is the solubility of the gas according to this form. So solubility of a gas is directly proportional to the pressure of the gas above liquid. So the one form is solubility of a gas is directly proportional to the pressure of the gas above the liquid. Second form is mole fraction of the gas in the solution is proportional to the partial pressure of the gas over the solution. And the third is the partial pressure of the gas in the vapor phase is proportional to the mole fraction of the gas in the solution. So these all the three forms are similar. Only changes we'll observe is in proportionality constant. So we are going to use the third one, the partial pressure of the gas in the vapor phase P is proportional to the mole fraction of the gas in the solution, which implies P is directly proportional to X, that is mole fraction of the gas in the solution. Or we can say P is equal to a constant is proportionality constant is introduced, this. So this is known as KH is known as Henry's law constant. This X is mole fraction of the gas in the solution or the dissolved gas, mole fraction of the dissolved gas, and P is the partial pressure above the solution, partial pressure of the gas, dissolved gas above the solution. So the units of KH this time will depend on the unit of the pressure we are using. Since mole fraction is a fraction, it has no unit, so the unit of Henry's law constant will be the unit of pressure which we are using over here. And the solubility may be expressed in other concentration terms also, like molarity, ppm, parts per million, or any other concentration units. But here we are using the solubility in terms of mole fraction, and this constant depends upon unit of the constant depends upon the partial pressure, units of the pressure only, and not on the mole fraction. If we have used instead of this mole fraction, the amount of gas dissolved are measured in terms of molality or molarity, then the units of the KH will be different. So in our textbook we are using this form only, that is solubility in terms of is measured in terms of mole fraction only, therefore the KH will have the units of P. So Henry's law implies that higher the pressure, higher the partial pressure of the gas over here, more the gas will dissolve. If the partial pressure is lowered, the amount of gas dissolved gets lowered. And if the partial pressure is increased, the amount of gas dissolved will increase. So units of Henry's law constant will be that of pressure, since the mole fraction has no unit, so KH will have the units of P, and it could be bar, atmosphere, pascals, etc. Henry's law constant, the value may be obtained by measuring P and mole fraction of the gas. So we can infer from this equation that this is the solubility of the gas and this is Henry's law constant. So there is a inverse relation between the Henry's law constant and the mole fraction of the gas. So higher the value of Henry's law constant, lower will be the solubility. Higher the value of the Henry's law constant, lower will be the solubility of the gas. And if lower is the value of the value of this Henry's law constant, higher will be the solubility. So some gases with very high KH value like N2, H2 are less soluble, and the one like CO2, SO2, HCl, their KH values are very small in comparison to other diatomic gases, and their solubility is high. So thanks for watching in this video, and in the next video we'll come up with applications of Henry's law, and we'll deal with some numericals based on Henry's law.